we're demonstrating ultra-high magnetic field reliability testing for NVE's medical-grade switch sensors. The parts being tested are NVE's 1.5 volt and 3 volt medical-grade magnetic switch sensors. The PCB on the right holds the 5 pairs of sensors being tested: the BHL925SP, the BD027, the BD032, BD121, and the BD129. All NVE medical-grade sensors are MRI-safe, meaning they cannot be damaged by magnetic fields up to 9 Tesla. However, some sensors cannot maintain the correct output state at high field strengths, beginning usually at 40 millitesla or 400 Gauss. Sensors that are designed to maintain the correct output at large fields are MRI-correct, in addition to being MRI-safe. This is what we are testing for. The device used to produce the large magnetic field is a liquid helium-cooled superconducting magnet made by the Janis Research Company. The particular system you see here is owned by the Department of Chemical Engineering and Materials Science at the University of Minnesota Twin Cities. The Janis magnet produces magnetic fields as strong as those produced in an MRI machine. This is a clip demonstrating the strength of an MRI's magnetic field with a steel chair. The part of the Janis system above the floor is only cryogenics equipment. The actual magnet is slightly below the floor. Because the magnet is under the floor, this long rod must be used to place our parts close to the magnet. The PCB holding the parts is placed into this dip socket at the end of the rod, which you can see happening here. The rod is then inserted into the Janis system. The voltage pins of the magnetic switch sensors are broken out to this box through the wiring of the rod, and B and C cables are connected for individual part voltage measurements. The other ends of the cables are connected to power and a data acquisition card. Here we have the wiring set up, and we are ready to begin taking data. The Janis system is here, behind the B and C cables. The magnetic field magnitude that the parts are subjected to is displayed here. And the LabVIEW front panel with the output voltage of all the parts is here. The top left and top right LabVIEW charts can be ignored. They are for calibration. The other 10 charts show the sensors of interest. The BD027 parts are our control sample. Here, we begin increasing the magnetic field. All the parts switch to their on state, which results in a low voltage output. You may have noticed that the BD027 started in the on state, then went off, and then on again, while the other 8 parts simply started in the off state and then switched on. This is because these particular BD027s have a slightly lower operate point than the other parts, and, being omnipolar, were switched on by a magnetic field offset of a couple Gauss in the direction opposite to the intended field direction. This field offset quickly becomes negligible as we approach large field values. At 500 Gauss, all 10 parts are in the on state. At 1 kilogauss, or 0.1 Tesla, the 8 MRI-correct parts remain on, but the BD027 control samples switch back to the off state. This continues all the way up to 90 kilogauss or 9 Tesla, an impressive feat, demonstrating their suitability for withstanding MRI fields. Here is a close-up of the charts. The MRI-correct parts are the ones highlighted in blue. We can see they are in the on state because the open drain outputs are sinking current, resulting in a low output. The bottom left and bottom right charts are the BD027s. They have a 2 volt high output, meaning they are in the off state despite the large field. We now decrease the field back towards 0. Around 800 Gauss, the BD027s switch back to the correct state of 0 volts output. At around 30 Gauss, all parts switch back to the off state, resulting in a high output of 2 volts, which is correct behavior. Here is a close-up of the charts at 0 field, with the 8 MRI-correct parts highlighted again. NVE's medical-grade magnetic switch sensors have operate points as low as 1.3 millitesla, have low hysteresis to prevent magnetic latching, are very low power, as low as 30 nanowatts, operate in a temperature range from -40 to 125 degrees Celsius, and come in a miniature 1.1 mm by 1.1 mm DFN4 package. Call, click, or email for more information about NVE's remarkable sensors. Lastly, I would like to thank the University of Minnesota Twin Cities Department of Chemical Engineering and Materials Science for allowing and aiding our use of their cryogenic superconducting magnet.